Hi, everyone. My name is Jess Garms. I work at Twitter. My teams work on the iOS and Android apps. I'm here to talk about unreliable networks. Now, there's no silver bullet for fixing problems that we have with the kind of networks that we see around the world and the troubles that we experience. But I'm going to break it down into sort of 4 different areas to discuss today. Reliability, resiliency, performance, and empathy, and what you can do in your own apps to try to improve the handling of your network issues. Now, let me define a little bit what an unreliable network really is. All networks ultimately are at least somewhat unreliable, but around the world we see different levels of reliability. It's correlated well with speed. That is, if you take a look at this map here that shows network speeds around the world, you can see what the most reliable networks are. And then the areas that have trouble are those that are much, much slower, and they have higher latencies as well as higher failure rates. And in those countries, people then see more network failures and they have more trouble. But it's not just in those areas that we have these kind of network issues, but in the first world as well. When you get on an elevator, when you get on the subway, you see the same kinds of failures that you would when your cell tower is overloaded in a place like Mumbai. And those problems then have similar solutions in both situations and can be improved greatly. Let me talk about reliability first. This is sort of a simplified diagram of how a network call gets made. And you can see the first step that we make is a wireless connection to a cell tower and then an internet connection to a server. And that wireless connection is where we typically run into failures. That's where you change from Wi-Fi to cell, or you change cell towers, or you're briefly disconnected as an elevator closes. Many things can cause that disconnection. But most of the time we think of the network as just being this infrastructure that always exists and just works. All of our diagrams kind of look like this. We make a call to the server and the server returns with a response. And that's the easiest way to build your application. You just make a network call and you look at the result and then it succeeded or it failed. But the problem is that the failure can occur in the network at any point along that round trip, either to the server or on the way back. And I'll talk a little bit about how to deal with both of those problems, but they occur all the time. Now, what happens if a failure like that occurs in your app? Typically, we just fail. The naive way of writing an application, you look at the response, you get an exception or you get an error of some sort, you just display an error like this. Sorry, couldn't send that tweet. Maybe at best you offer the user to try again. But the thing is that really is what everyone wants to do, is just try it again. And so what we can do is just do it for them. And so we can look at the response and actually decide, is this something that could be transient? And if it is, we'll just immediately retry it for the user. And what we do is we set up an exponential backoff to make sure that we don't waste battery or network, and then over time, keep trying. At some point, we have to give up and fail, which depends on the kind of action that we're taking. But what we found was that simply by having a retry like this for transient conditions, we could decrease our failure rate by up to 80% in some markets. But you have to be careful when doing this because you don't want to retry every possible failure, but only the kind that can actually be retried. On iOS, what we do is we look at the failure codes from our responses and look for things that we know are potentially transient. Things like we couldn't find a DNS entry, we couldn't reach the host, we couldn't send our data, and only retry in those conditions. Android is a little bit different. On Android, when we try to read from the network, we can basically catch any I/O exception that happens when reading from the network, and those are all going to be transient failures. They're like, no route to host exception, DNS exception, a socket timeout exception, and then typically it's safe to retry. One thing you just have to be careful when doing this is not to mix your reading and writing to disk in the same block. You can then notice a local failure, think it's a network failure, and accidentally retry it, which I would not recommend. But when you do these retries, one thing that's very important is idempotency. If you were to naively retry every single request that you might send to the server, sometimes what happens is that the request itself got through to the server, but it was the response that you failed to read. And therefore, from the client's perspective, it looks like the network request failed. But from the server's perspective, everything looks just fine. And so you could then send the same request again, and you end up with the same result, that in this case, 2 tweets with the exact same content. Typically not what the user intends. There are several different ways to address this depending on the kind of data that you're dealing with and the kinds of requests that you're making. One that's very nice is if you have some kind of natural foreign key that forbids duplication. So in our app, favoriting a tweet, for instance, is something that can only take place once. Either you've favorited a tweet or you haven't. And so if we receive a second request to favorite the same tweet, we know we can just ignore that, return success, and then carry on. Another option is to detect duplication on the server. So for instance, in this case, we can detect that the same image that was uploaded earlier is trying to be reposted as a tweet, and that's the only content. So we can match that request was made earlier and return success and not bother reposting it. That's a little tricky though, because it means that you have to keep a cache server side of the requests that are recent, go through them and compare, and it's very specific to each request that's being made. Another better way to do this is by tagging the request with some sort of GUID, so that you can then determine this. The client can completely invent a request ID, send it up to the server. Server can see if this request has been processed before across any instance, and then return whether or not that's already taken place. Let's see here. Another aspect of retrying and reliability is resiliency. In a case where we're unable to send the request in the first place because we've lost network connectivity, we don't know when the network is coming back up. It might be back up in seconds in the case of you've just gotten onto an elevator, or it might not be back for minutes in the case of a subway car, or maybe it's hours because you've gone into Wi-Fi mode and you're about to get on a plane and you're not going to land for a long time. And so the user isn't necessarily going to keep your app open and keep retrying. Lots of things can go wrong. They could background the app. The OS could decide to kill the app because it's running low on memory. The app could actually crash in the background or the foreground. We really want to make sure that at no point do we ever lose this request simply due to our retry policy. The user kind of expects that they've taken an action and it's going to then show up on the server. And so what we do is we make sure that we write the action to disk before we then send it on the network. And now, in our case, we haven't done that yet with all of our actions. It's something we should do. But so far, we've started with the most important action, which is tweeting, and we make sure that that's stored. And then eventually, we'll build up a larger framework that will allow retrying for everything and resiliency for everything. Now let me talk a little bit about performance. As I mentioned earlier, these networks are not only unreliable, but they're also slow. And there's 2 different kinds of performance that we look at. One is objective, and one is perceived. Objective is easy to look at. You just measure how long it takes for something to occur. How long does it take to upload a photo? How long does it take for a network request to tweet? How long does it take to fetch the timeline purely on the wire? But perceived performance is what really matters, and it's a lot trickier to define. This is how long it feels for a user when taking an action. If they press the tweet button, how long until they think their tweet has gone through? If they favorite something, how long until the UI responds? If they're loading images, how long until they get some sort of feedback? And so it's very important that we look at and try to solve both of these as best we can, regardless of the network condition. And they vary based on the action that you're taking as well as the conditions that the phone is in. For objective performance improvements, one of the things that we did is we added additional points of presence around the world. These are basically places where we can terminate our SSL connections as well as serve up images from our CDNs. And so by putting these into individual markets, we can actually bring that network connection a lot closer to a user. The speed of light being what it is means that it takes at least 130 milliseconds to get around the world and back from a remote location. But typically it's actually much, much worse than that. We often see round trip times of up to 2 seconds from India on 2G. And so just by moving the connection much closer, we can make the app much snappier, objectively so, and we can pump more data through more quickly. But we can only move some of the data closer to them because some of the requests have to go back to our data center in order to retrieve them. But SSL, for instance, is something that we can do locally. It requires several round trips, so moving it locally makes a lot of sense. Same thing with CDNs. It's not sensitive data. It's not specific to a user. They just need a URL. It caches quite nicely locally. Additionally, one of the things that we did is we migrated away from HTTP 1.1 towards SPDY and soon to be HTTP 2. This is a new protocol that replaces HTTP and basically has a few advantages over standard HTTP. The first thing is that it allows out-of-order responses. So if you share a single HTTP connection and you're trying to make a request for, say, the timeline, as well as an image, as well as favorite a tweet, typically in HTTP 1.1, whatever the first request that went out was, we have to wait for the entirety of the response for that. In the case of a timeline request, that's rather large. It can be tens of K in size. We'd have to wait for the entirety of that before we could get back the response for the tweet or, say, tweet details that a user might be waiting on. So what SPDY and HTTP 2 do is they allow those responses to be returned out of order in chunks. And so we can actually then interleave those, and whatever is smaller can arrive sooner. Additionally, HTTP 2 allows for prioritization. So we can actually indicate in a request that this is a high priority request and ask the server to return it more quickly than the others. And so we'd never get blocked based on other requests in the pipe. And then last, there's header compression that HTTP 2 does, which helps a lot just in reducing the size of each request and response, thus improving objective time. Now, in addition to improving our APIs and their speed, we also looked at image loading. And one of the things we found is some of our images are a substantial amount of the bandwidth that our users use, and so it's very important for us to decrease their size without decreasing quality. And so one of the things that we looked at was WebP, which is an alternative compression format from JPEG. It's invented by Google several years ago, and basically allows for the same level of quality at a savings of between 30 and 50%. Unfortunately, it's only supported on Android version 4 and higher, and even then, only some formats of WebP are supported up until, I think, the second version of Jelly Bean. And so it only has some application. But in our case, it made a big difference in bandwidth usage. And so we began deploying this out to our Android 4.0 clients and higher based on what they could support. So for instance, if they could support lossless WebP, we'd use that. If it was only lossy, we would use only that version. But it also costs more to encode and decode than JPEG does. It's about 10 times more expensive to encode and 1.5 times more expensive to decode. What we found when we experimented with it is that that was more than made up for by the decrease in size. Because we decreased latency so much, the users got a faster experience, and caching was no more expensive than JPEG. In fact, even a little smaller because the image was smaller. So even though the actual encoding time was more, it ended up being amortized by sending off to several different clients. Unfortunately, iOS doesn't support WebP. And so we couldn't then share that same WebP image format with iOS, at least not natively. We would have had to write our own decoder. And so that meant that our network caches were somewhat fragmented. Again, not a problem for the number of users that we were seeing, but as we break down into finer and finer versions of images and phones, it becomes a little bit of a concern. We wouldn't really want to use too many different variants, or else our caches would start to lose their value. On iOS, what we did is we took a look at, instead of using WebP, using progressive JPEG. This is a format that isn't really any smaller than JPEG, but it allowed us to show something to the user much, much faster. In some cases, it would only take 25% of the time to show that initial pass of a low-res image, like you can see on the left-hand side. It's not nearly as nice as the right-hand image, but it's a much better experience to not see a gray box and instead see something. And fairly rapidly, usually by the second pass, we'd get a fairly high-quality image that was usable for users. In places with something like LTE, we didn't find that this made a substantial difference because the connections are already so fast. But on a 2G connection, this is a huge win. On Android, like I said, we used WebP, but we were intrigued by this idea of progressive rendering. Because Android is so popular in countries that have 2G connections, it would be great to get some sort of progressive rendering. Unfortunately, Android doesn't support progressive JPEGs natively, so we started looking at ways to do that. There is a Facebook open source library called Fresco. It's an image pipeline that does do progressive rendering. So that's one possibility. And then we're also looking at a few other things like JPEG 2000, but we haven't quite solved progressive rendering on Android yet. So because of that, we went down a different road that was a little easier initially. That is using a low-res image before the high-res image on really bad connections. So we could look at the connection and say, all right, this is basically a 2G equivalent connection. So what we're going to do is download like a 100 or 200 pixel wide image at very high compression and display that. Once that's displayed, then we can decide whether or not to grab the high-res image based on their connection and the cost of their data. And we found this was also a huge win in terms of latency, similar to progressive JPEG, though it does bring in the cost of an additional image being loaded. And so we want to make sure that we don't grab that image if we don't need to, like on an LTE or Wi-Fi connection, we'll typically go straight to the high-res version. We're still experimenting a bit with this one. We haven't rolled it out fully everywhere, but so far the results look intriguing. A little bit more about sort of perceived performance is that waiting for requests is really annoying as a user, right? You send a request and nothing happens, you don't know what's going on. And one of the problems that we found was that typically our timeouts were set quite high in the app. That because initially we had not done retries, we discovered that the longer your timeout was set for, the more likely your request was to succeed. The user might get frustrated, but you still would have eventual success more times. And when we looked at the data, we found that 98% of our requests in the US finished in under 3 seconds. And so it wasn't really buying us much with retries to have a long timeout. Instead, we could crank down the timeout to a much lower rate and then see faster successes, even in the case of a failure followed by a retry. But what we needed was some way to expand that timeout when it was necessary. If the network is really slow, you don't want to keep retrying every 3 seconds. And so what we did is a dynamically based timeout based on if we got a timeout exception on the way back, we'd then try to double our timeout, a timeout exception again, we'd double again, hopefully ending with a reasonable retry or a reasonable timeout. And in a place where we know that the network connection is bad, like India, for instance, we'll start with a timeout that's longer, more like 30 seconds, because many of our requests won't even finish in that initial 3-second timeout. Another thing that we do, and we've only really started to do this recently, is request prioritization. Typically, our app is making a lot of requests at the same time, both foreground and background. We've got a timeline request, you might be favoriting something, we're scribing some data up to our servers so we can analyze that data later. Maybe we're doing some prefetching, we're polling for the timeline, everything all at once. And we found that we could actually sort of gum up our own requests that the user is waiting on based on other things that are going on. And so what we wanted to do was find some way to instead tag those requests based on how important they are to the user. And so, the first thing that is most important is any action that the user has taken, especially any data that they're trying to send up, like tweeting. Favoriting is also important, retweeting, things that they're going to really, really notice. The next thing that's most important is foreground API requests. So for instance, you refresh the timeline, you go to a tweet detail page, you're waiting on something in the UI and you want that to respond quickly. And then images loading, if you've used Twitter, you'll see often, we can load the timeline first and then load images more lazily as that comes in. So the user still sees some content, but the images are next that they're going to want to see. And then after that are those background API requests that the user hasn't really done themselves, but maybe they're fetching the timeline in the background, maybe we're posting some data. And then last is that kind of prefetching stuff that the user isn't even really aware of, but we're trying to give them a better experience by fetching some things in advance. And so far, we've only rolled this out in a very limited way on iOS and Android, where on iOS, it only affects some of the queues that we have locally. And on Android, we only have kind of one basic prioritization for tweeting and then everything else. But we're gradually making that more sophisticated, attempting to achieve this level. And a lot of what happens is that we queue up actions inside the apps. And so what we want to do is make sure that we look at those queues before we pop the next thing and grab the highest priority item. But this is definitely a work in progress. The next thing about perceived performance is really letting the user know what's going on. The most frustrating thing is posting a tweet and not knowing what's happening. If the tweet is going to get, is it going to get posted? Has it disappeared? Has it failed? What's going on? And so we found that just by adding a progress bar and sort of a grayed out tweet at the top of the timeline, we could reduce this anxiety. We found that people were actually tweeting more often once they got this feedback because they were confident that their initial tweet had taken place, and so they were confident then to make more tweets. It's also just having used it in various locations, it's just a pleasant experience. You understand what's going on, and you're not just wondering what's taking place. There are some network actions, though, that aren't really worth communicating to the user what the status of the network is. If you favorite a tweet, you don't really need to know that your request is kind of queued up or it took a couple of seconds. You just want to immediately change the UI and give the user positive feedback, and then the background keep processing that request. Usually it returns very, very quickly, but it's still slower than the feedback that we can give the user immediately. And also different actions have different things we need to do when an error occurs. So if an error occurs right away, we can show a user some sort of dialogue or indicate in some way that something went wrong, especially if there's something that they can do about it. Like for instance, if they've been logged out, we can then prompt them to log back in, things like that. But there are some actions where it's too noisy to tell the user everything that's gone wrong. And so for instance, you can imagine if you've favorited something and we're retrying and retrying and retrying, but you've been in offline mode for hours, then at some point we have to discard that. We have to decide, well, do we show the user an error indicating that that failed, or do we just dispatch it at some point? And so there are certain actions where we feel it's just not important enough to rise to the level of telling the user. And so instead we should just try as hard as we can to get that action through. Because of course what the user would do is typically just retry that action anyway, so we need to just do that for them and not give them an annoying error. One of the things that we've developed in trying to figure out how best to respond to network problems and how to improve perceived performance is to actually look at our network quality and then try to make decisions on what our UI should do based on that quality. And so we measure the speed of our network, we measure the latency of all the requests that we make, and then give all the developers working on top of the app the ability to make choices in their UI or in their actions based on the current conditions. So we basically just have 4 kind of network conditions. There's no network at all, like when we're certain that there's no network, like you're in Wi-Fi mode, or you have no SIM card and no Wi-Fi. There's poor, where we see that some requests are potentially getting through, at least things are getting out, we're getting limited data back. Then we have a good connection that's more like a 3G connection or higher, and then last, an excellent connection where you're on a good LTE connection or a good Wi-Fi connection where data is coming down very, very quickly, and basically you can do almost anything you want. Additionally, we have APIs that we've built that allow you to determine whether or not the user is in what we expect to be a cost-sensitive region for data. And so we know, for instance, if a user is in India, we probably shouldn't use a lot of their bandwidth for prefetching content unless we're absolutely certain that they're going to use it. Now I want to talk a little bit about empathy. One of the things about using the app inside the Bay Area and in San Francisco or Seattle is that your network connection is very, very fast. And typically, everything succeeds very, very quickly. And the only time you see those failures are in those limited situations where briefly you have some sort of outage. And instead, we really need to understand what our users are experiencing all the time around the world. And one way we do that is measuring it. And originally, a lot of our measurements we looked at were data from the servers. We'd see, what was our success rate inside the server, inside the data center. And those success metrics were very high, of course, because once the request made it into the data center, it was very rare for us to have a problem on the back end. Like, we'd typically respond well unless there was some massive outage, in which case everyone was on top of it, fixing it, and then the success rate would go back up. But instead, what we really need to do is measure from the client's perspective. How often are we succeeding? How long are these actions taking? And then how can we break that down by area, by phone type, by OS, and really, really look at what our users experience? And then what we need to do is then be able to take a look when we try things that we think are going to improve the experience. We must measure that to make sure that they actually have an effect. Several times we've looked at various timeout policies, for instance, and thought that we would have something that would work very, very well, deployed it into the real world and discovered that it in fact wasn't the case, or that it would help in one area but actually make things worse in another. And so we'd have to go over the data again and again in order to try to understand what's really happening for our users. Another tricky thing to measure is gray box time. This is something where it's not as easy as just measuring how long a request takes. What we really want to see is how long does a user experience a particular condition. In this case, we have these blank images. They've managed to get a timeline, but they haven't seen the images yet. And so the user scrolls up, we show a gray box for some period of time, and then either they scroll away from the gray box, which we count as a failure, or the image eventually downloads, which we count as a success. And so we need to measure how long is that gray box shown, and then which transition it makes, because we want to increase the success rate, but we also want to decrease the amount of time that it takes. And we don't want to count scrolling away as a success, because just if a user scrolls away faster, that does us no good whatsoever. And so if we were to do something like progressive loading, we expect that we'd see a good decrease in gray box time, but potentially no change in overall success rate. Maybe we wouldn't see the images fully load any more often because the user might still be scrolling at the same speed, but we need to look at this data to see if that's the case. Another thing for empathy is looking at what exactly the network is doing. So we ended up building our own tools to keep track of all the network requests that we're making and their responses, and then be able to look at it in this sort of graph you can see here. And this allows us to see how much time is spent blocking in the queues of the app, how much time is spent sending data, how much time is spent receiving it, how much time waiting. And this has often let us diagnose some really tricky problems. And we've just started looking at how we can roll this out for error reporting in production, but mostly we've done this for ourselves, for dog fooding, for debugging, and things like that. And it's been useful even in that regard. But sometimes we see users that experience some problem in the wild, and it would be great to get back something like this from them so we could see, did a request take a really long time? Were any requests getting through? Was just one failing? It gives us a lot of data. And we have this on both iOS and Android. And so we'll often share these between the two to try to understand the behavior of each and see if there are things that we can do on one to make it behave more like the other when that seems like a better behavior. Another thing that we added was a network simulator to the app. And so this allows us to basically add latency or reduce the bandwidth inside the app so we can see what the experience is like, more like our users in other places. And so this has allowed us to really get a feel for the app better. It's kind of limited right now. We can change bandwidth, but it only affects our SPDY or HTTP2 connection. And so, for instance, it doesn't slow down the web browser that a user might open, which is also a real problem in other markets where the web itself is slow, not just apps. But it's been great for building empathy, and it's been something that we've been able to then show to other teams when they want to see how their feature works in these kinds of conditions. And that's pretty much it. Really what needs to be understood about this is that the network is just slow everywhere. And some places it's incredibly unreliable, but everywhere it can fail. And there isn't a single thing that you can do to just fix that. Instead, you've got to look at the uses of your network everywhere along your app and improve each of the things that you can, whether it be objective performance or perceived. You need to make the app just feel faster and better. And that's it. Thank you.